Okay, good morning, everybody. We're Los Huracanes, and we will be presenting an upgrade of Wastewater Sistema Central in Havana, Cuba. My name is David Hernandez, and I'm the project manager of this group. So a brief overview of the topics we'll be covering today. The current Sistema Central and the conceptual alternatives and population flow will be covered by Laura Vogel. The water quality classification maps, the bathymetry, the pipe material selection will be covered by Lucien Gassie. The outfall design will be presented by Yifan Zhang. The wave forces and ballast design will also be covered by Lucien Gassie, and I will be covering pump specification, preliminary treatment, and construction aspects.
Sistema Central is the largest sewer system in Havana. It was originally designed to accommodate 600,000 people. However, it is now serving over 900,000 people. The wastewater is collected in the main lines here in Collector Sur and Collector Norte. The wastewater is then transported to Muelle de Caballería, where it undergoes preliminary treatment, including bar racks and grit chambers. The wastewater then flows in a 2 meter by 2 meter square tunnel, which is approximately 1.4 kilometers long, to the Casablanca pump station, where it is pumped up through La Cabaña and out to the existing outfall that is currently at Playa del Chivo. The system is over 100 years old and past its design life. Thus, it is necessary that something is done to improve the current situation. We at Los Huracanes will be focusing on upgrading the outfall at Playa del Chivo. In order to properly model the proposed outfall, we need to determine a design flow rate. Sorry. Did I skip a slide? Okay. Well, first, before I go over the flow rate, I'm going to go over some alternatives for you guys. Several alternatives were considered prior to identifying the preferred option. The first alternative was to maintain the existing system. This alternative was disregarded since the existing outfall is over 100 years old, as I spoke of earlier, and in such a state of disrepair that maintenance would be insufficient and an upgrade is required. The second alternative was to design an outfall that discharges at a sufficient distance from shore where there are no water quality standards to be met. The advantage of this is that there would be no chlorination needed. However, this would be too deep for construction because it was calculated that this would have to be at a depth of over 100 meters. The third alternative is to construct an outfall to a depth of 45 meters using an open pipe. This was disregarded because the dilutions attained were calculated to be insufficient to meet the coastal water quality standards in that area. The fourth alternative was to recycle the water. This would require us to abandon the outfall system and design new primary, secondary, and tertiary treatment. This idea was disregarded because there's not enough information on the feasibility or interest to defend the high costs in this area. Lastly, the fifth alternative was to design an outfall with a diffuser to meet ambient water quality standards with a design period of 30 years. The advantage of this option is that it uses most of the existing infrastructure while replacing the most critical part of the system. This is the option that we pursued because it was the most desirable alternative for the Havana area. Now we'll talk about the population and the flow. In order to properly model the outfall, we need to determine a design flow rate. The current flow rate is 2.01 meters cubed per second, and the calculated design flow rate was 6.68 meters cubed per second. As you can see from this graph here, the expected population is expected to decline over the next few years. Thus, we designed for the current population of 2.4 million people. In order to compensate for the improved hydraulic capacity of the system, we went with a conservative future per capita flow rate of 570 liters per person per day, as opposed to the current per capita flow rate of 186 liters per person per day. We believe that this design flow rate, which is 3 times the original, should be able to accommodate the future needs of the Havana area.
On the screen is the water quality classification map. There are 3 classes in our area of interest, class B, D, and E. Each of these classifications has many components of water quality requirement. Our proposed outfall will meet all of these through dilution except for the fecal coliform water quality standard, which will be met through disinfection. Class B waters consist of beaches and coastal areas and are located east of Playa del Chivo. These waters have a fecal coliform water quality standard of less than 200 colony forming units per 100 milliliters. The Class D waters are marked as industrial uses and are located on the coast west of Havana Bay and also surrounding the Class E waters. These waters have a fecal coliform standard of less than 1,000 CFU per 100 milliliters. And finally, the Class E waters are for port activities, and they consist of Havana Bay and the surrounding area, and they also have a fecal coliform requirement of less than 1,000 CFU per 100 milliliters. So here's a close-up map of the proposed outfall and the existing outfall. As you can see, they're located in Class E water, but it is also important to consider their effects on the Class D and B waters, which are nearby. The proposed outfall is located adjacent to the existing outfall so that it can be easily connected to the existing infrastructure. In addition, the proposed outfall consists of a diffuser, and the wastewater will be disinfected to meet all of the nearby water quality requirements. The bathymetry data was obtained from a map created by the U.S. Navy and the Public Works Ministry of Cuba, and the depth profile of the existing outfall is shown in the image. As you can see, the existing outfall is currently an open pipe, and there is inadequate dilution and treatment to meet the water quality standards. Due to the limited data, we assumed the depth change to be linear between the contours, but it is most likely the seafloor is rocky and uneven instead. Also, the ocean environment is unstratified, meaning that mixing will occur throughout the water column. So an important aspect of designing the outfall was the pipe material selection. We decided to go with high-density polyethylene, HDPE. There are several benefits to this material. It's strong, flexible, durable, lightweight. It also has low transportation costs, and it's easy to install. It is typically either shipped in 12-meter sections, or it can be shipped as one large 500-meter section. And to install it, it's just floated out, towed out by a boat. The pipe will be empty, and it will have the concrete ballast around it. And to sink it, it's just filled with water when it is in position.
So we took these hydraulic constraints into account when we designed the diffuser, because we want to make sure that as the effluent is discharged from the diffuser, there will be no deposits there will be no solids depositing in the diffuser. And secondly, we want to make sure that the pipe is full and full. And thirdly, salt water will not be able to intrude into our diffuser as the effluent is being discharged. So as the wastewater initially gets discharged from the diffuser and being diluted, we classify the environment to which it is discharged as the near field. And the amount of dilution is calculated with this equation shown right here. And our design diffuser is designed to have a total of 12 ports in total, and the dilution is calculated in this right column here, showing the dilution across each port. And the average dilution came out to be 107:1, which is more than what a secondary treatment can achieve. The other parameters shown here in the table is what we use to design our diffuser and to verify that our hydraulic constraints are being met. Here is a 3D and 2D drawing showing our design diffuser. As you can see here, the diffuser is designed to be a total of 120 meters long with 10.95 meters spacing. It is spaced so that the plume will just merge as the surface to the surface of the ocean. And then as you can see, the diffuser actually narrows down. The diameter narrows down as it extends out because we want to ensure that the flow rate will be equal across each port, the discharge rate. So here is an image showing the design outfall with the diffuser being located above 45 meters deep because as soon as we go above 45 meters deep, we would have to require very expensive and complex diving cost for our maintenance and construction issue. So we wanted to avoid that. So we think now it'll be a great time to show you our physical model to further demonstrate the mechanism of the ocean outfall.
So this will be So as you can see here, this is a great model to show our near-field design. And what will happen is the wastewater will flow through our multi-port diffusers, and it will cool off as such. As Yifan explained before, the multi-port diffusers make it nice for dilution to achieve the dilution necessary for the model. And it could go up buoyancy driven, where it will reach the far field and become wind driven. So we could leave this running here. Is it in the way, or alright, so we'll continue on.
Okay, so as David just demonstrated, our ocean outfall will be able to achieve a dilution of 107 once it reaches a design flow rate of 6.68 meters cubed per second. But upon construction, with a current flow rate of 2 meters cubed per second, we'll still be able to achieve a much higher dilution than our design dilution, which is 107 to 1. So throughout the process of the current flow rate up until the design flow rate, we will be able to achieve our design dilution. So as you can see from the model, after the near field mixing occurs, the plume will start to rise to the surface, where it starts to be dominated by ocean currents. And that's where the far field mixing occurs. And we use this equation shown right here to calculate the concentration of the effluent in the far field. We also use this equation to delineate the boundary of mixing zones, which essentially delineates where our water quality standards are being met. And as you can see from the two images shown here, image A, the red dotted line corresponds to a ambient water quality standards of 1,000 fecal coliform counts per 100 mils of seawater. And beyond the boundary, all ambient water quality standards are met. And also in figure B, the red dotted line right here corresponds to a 2,000 fecal coliform counts per 100 milliliter of seawater. And also beyond this boundary showing right here, our water quality standards are being met.
To calculate the wave forces on the outfall, we used data from the National Data Buoy Center, buoy 42002, which is located approximately in the direction of maximum fetch or wind-wave interaction from Playa del Chivo. This buoy had 37 years of wind data, and we fit the maximums to a Dagom distribution and used that to calculate the 50-year design wave. After that, the Morrison and lift force equations were used to calculate the maximum wave forces on the outfall. So the concrete ballasts are important for a couple of reasons. Without the ballast, the pipe and its contents are lighter than seawater and would tend to float to the surface. Also, the ballast serve to stabilize the pipe from oceanic forces. We size the ballast by total force analysis on the pipeline. And also, it's typical to bury the pipe in the wave breaking zone. So we did a preliminary cost analysis of excavation costs versus concrete costs, and then applied a safety factor of 1.5 to account for pipeline stress on the wave breaking zone. After that, it was determined that the pipe would be buried to a depth of 15 meters, after which the concrete ballasts would be used. 11 ballasts would be required in this calculation, and the dimensions are shown in the image. And they also have a thickness of 3.5 meters.
So now I'm going to talk about the pump specifications. For the outfall we modeled, it's not going to be able to flow by gravity. Well, we'll need the use of pumps for it to flow to the correct design that we put in our design. So essentially what it is currently, the way the necessary pump is designed is by the amount of head necessary for flow, or the amount of energy needed. Currently, the amount of head needed is 2.23 meters, which is from up to sea level. The design flow will be 14.65 meter head. Keep in mind that this is just a sea level. Our water will be below sea level, so upon final construction, we will be able to determine how many pumps the level of pumps we need and how many pumps we need, as designed by the pump curve here, which will indicate how many pumps necessary. This is our system curve, which determines the amount of head or energy necessary for flow according to our design flow. For example, 6.68 meters cubed per second will give us a flow of approximately 14.65. So for preliminary treatment and disinfection, currently we do have bar racks and a grit chamber. We will utilize this to remove the solids, which will prevent clogging in the outfall. We will be using chlorination, and we will be using 10 milligrams per liter as a dose with a 30-minute detention time. The outfall will serve for 15 minutes of detention time, and we will also have a 1.5 million gallon tank located at Casablanca to provide the extra 15 minutes. This will provide a 99.9% reduction of fecal coliforms. Finally, we will discuss the construction aspects of our project. This image here indicates a typical installation of a outfall. Some factors to consider, one would be the weather conditions. Cuba is in the Caribbean, which is at risk for hurricanes. For this reason, we don't suggest that construction be taken between June and November, which is hurricane season, as I'm sure we all know that. The subsurface geology, as Lucien mentioned, it is rock. So there are a couple of methods of doing it. We could either go by drilling or by explosives. We decided to go by drilling because explosives, first of all, are dangerous and would require a level of expertise in that certain procedure. So we felt drilling would be the way to go. The pipe material, it was mentioned that we would be using HDPE. This is nice because it would float. It would be more practical to construct on land, where it could be then towed out to the location where it would then be filled with water, where it could sink to the bottom of the ocean and be put into place by the anchors. So in conclusion, our project will have a design life of 30 years. It will replace the existing outfall, which is currently located off the coast of Playa del Chivo, and could essentially be implemented immediately. The technology's there. This design life for the current outfall is beyond its design life. It's something that definitely needs to be done, and we feel like this is the best approach to it. And the approximate cost, keep in mind this is just preliminary, is approximately $8.2 million. Once the final design phase takes into effect, we could then get a more accurate cost level. But this is a pretty typical cost for an outfall of this size. And we would like to acknowledge Dr. Armando Perez, Jorge Martinez Pedraja, and Dr. Philip Roberts for their information and insight for our project. And with that, we thank you for your time, and we will open the floor to questions.